who has not got to the first two talks. Yeah, over to you, Ramakrishna. Sairam.
Can you see my screen?
Not yet.
Not as yet.
Okay, how about now?
Yeah, it's coming. I can see a blank screen now.
Okay, can you see me writing or?
Yes.
Okay,
yes.
okay.
Yeah.
Okay, so in the past few lectures, especially in the first lecture, we started with the question, what is physics? And we defined physics very rigorously. Physics is the study of physical things. Then we asked ourselves a question, what is a physical thing? A physical thing is something now, and it can become something else later. Being something now is its act or actuality. A physical thing is something actually now, but it can become something else later, and that is potency. So physical things exist and they can change. What do we mean by change? Change we defined as the process of potency becoming actuality. For example, let's say there is a ball here. It is here. That is its act. But it could be there. The ball could be there. That is its potency. The ball is here actually, not yet there. So we would say that the ball is here. But when the ball moves there and ball comes to this place, then the potency that was called there is actualized. So the ball moved. So that potency becoming actuality, what is possible becoming actuality, is what we call as change. So things exist and things change. This is the primary way to think about physical things. And the duration of change is what we call as time. So things don't change in a background called time. Because things change, there is time. And we have also seen the most basic primary property of a physical thing. The primary property of a physical thing is extension. That is, having one part next to another. No matter which physical thing you take, it has extension. It has one part next to another. And some physical things can exist by themselves. For example, you or me or a tree or a board. So these physical things exist by themselves. But there are some aspects of these physical things that cannot exist outside a physical thing. For example, let's see a quality called mass. Mass cannot exist outside a physical thing. It is a physical thing that has mass. So mass is a quality that is an aspect of a physical thing. Similarly, color. Color would be a quality or an aspect or a property of a physical thing. You cannot imagine color outside physical things. Light is also a physical thing. It is a property of space or akasha or plana, whatever we want to call it. And that space is a physical thing, as Einstein showed. So we wrote down the primary properties of a physical thing. The most basic property is what we call as quantity. This quantity doesn't really mean number. This quantity, by this quantity we mean extension, that is having one part next to another. That is what we mean by extension. So a physical thing primarily has extension, and then it has certain qualities. It's the way it is. It's mode of existence. So when we say an apple is red, that redness, that red color is in the apple. That red color has no existence outside the apple or a physical thing. You can have a red car or red something else, but it would be a red something. It would not be red by itself. That's only an abstraction. By abstraction, what we mean is we look at physical things and we can turn off certain qualities. For example, let's say you're looking at a wall that is painted green. Then you can consider green by itself in your mind, meaning you can turn off certain properties of the wall, like, the roughness of the wall, the texture of the wall, how the bricks are placed next to each other in the wall. All these you can abstract out. That is, you can turn these features off. You have taken this entire physical thing, whatever it is, that has gone into your brain, and your intellect can turn off certain qualities and just understand only the color itself. And that is what we call as imagination. That is, we have the ability to manipulate images. For example, if I tell you, you can imagine a unicorn with a chocolate horn on a mountain of water or something like that. You can still imagine that, although you will never see it in reality, because you have the ability to turn things off, consider things separate from the physical things in your mind as a mental construct, like how I can turn off other properties of the wall like texture or roughness and consider only its color. Like that, you can only consider certain things and manipulate them to put different images on top of each other, which is imagination. And this comes from the fact that a physical thing doesn't exist alone. It exists among other physical things. And so there is always comparison between multiple physical things. So these two are what we call as intrinsic properties of the physical thing. But we also have extrinsic properties. Those extrinsic properties are, the first one is relation. That is, I can compare one physical thing to another. I can say this table is longer than that table. So when I say longer, I am talking about the property of having extension. That is what length is. Length is having one part next to another. And then we have action, reception. This is not action and reaction. A physical thing has the ability to act on another physical thing. For example, you have the ability to push a ball. So you can act on the ball, and the ball has the ability to receive. In fact, the measure of that receptivity, how much momentum a ball can receive from a person or from a force, is its mass. We will see that later. But then we have environment. That is what it is surrounded by. And place, orientation, and then finally time. So time is an extrinsic property because change itself is extrinsic. So when we say change, it is what is not in the object. For example, if you look at this ball, in this ball, when I say this ball is here, you do not have there in the ball. The ball is here, which means the ball is not there. So there is not in the ball. But when the ball moves and comes here, then we say the ball has gone there. So acquiring something a thing does not have is change. And when a thing is acquiring something it doesn't have, that something it doesn't have must come from externality. Because if it already had that, it doesn't need to acquire it. If the ball already had the position there in it, then it doesn't need to move there. But when we say it is moving there, that there is external to the ball. So when we say a thing is changing, that change is external to the object. Because if that change was not external to the object, if that change is internal, then it doesn't need to really change because it already had that in it. I hope you are able to see my point there. So change itself happens because of extrinsic nature, because you have multiple physical things, and duration of that change is what we call as time. Now, from these properties of the physical things, we see that there are four important things. That is, every physical thing has a place, it has a certain orientation, it is in a certain environment, and it changes. So this is what we call as POET: place, orientation, environment, and time. So every physical thing has that, because every physical thing is extended and every physical thing changes. So it must be in some place, it must have some orientation, must have some environment around it, and it must take some time to change, that there is a duration of change. Now, given these foundations, our goal as physicists is to understand physical things, and one of the most important changes in physical things is motion. What is the definition of motion? Motion is change of place. So motion can be thought of as change of place. When I say change of place, this could involve whether it is change of place or change of orientation, change of environment. All these are included in that. So motion is change of place, and recall that change is potentiality or potency becoming actuality. So far we are only saying these in words. We have not started to capture any of this in mathematics. So how do we do that? How do we look at a physical problem? Like, is there a question?
Okay. When you say orientation,
yeah.
So for spherical objects, how do you understand that?
It is oriented some way. Even a spherical object must be oriented some way in space. It cannot be by itself. There is, when you are thinking about inside the object, so the spherical object itself be outside it, and the spherical object itself must exist somewhere, and it must exist, along certain direction in space. So it must be somewhere. So it depends upon where you're looking at it from. We are not talking about internal orientation of parts, but whatever this physical substance is, whatever this physical thing is, it exists, and it must exist at some particular place.
Because it's isotropic, so I'm just thinking, okay.
You are thinking about isotropic. I would highly recommend not using any words like that and start from fundamentals, that you're already in some sort of an abstraction. I highly recommend that come out of that abstraction and consider, how would you know a physical sphere? It should be somewhere like an orange. It should be somewhere like Earth. It should be somewhere. It must be embedded somewhere, right? And so, for example, let's say you are looking at it from the moon. This Earth is in a certain direction. It's in a certain orientation. If you go this direction from moon, you go to Earth. If you go opposite direction, you don't go to Earth, right? And similarly, from the sun, it's in a different orientation than the moon. And from another planet, Jupiter, it would be in a different orientation. So Earth is a sphere, but it itself is embedded in physical space, and so it will have some orientation based on the vantage point that one is looking at. Within the sphere is what you are thinking about, sphere as an abstraction. By turning off all the other qualities, you're turning off all the other qualities, and you're thinking that the sphere as a mathematical abstraction without any qualities, just as an idea. And in that idea, you are saying that it looks isotropic. But don't think about ideas. We are talking about physical things. So physical things like a physical ball or a physical sphere must exist somewhere in space. I hope that sort of makes sense.
No, I have other views. Anyways, continue. Let's not stop careful.
Okay, so any physical thing must exist somewhere, right? So and so it must have a place, orientation, environment, and time. And so we want to use these to capture the motion of any object, of anything, right? So now let's start with a simple example and see how we can mathematize to build stuff that we can build mathematics such a way that we can describe this motion. That we cannot completely describe it, because as we will see, we are going to lose the essence of motion. So let's say there is a hoop. Let's say this is a circular hoop, so of some radius, and let's say there is a bead on top of this, and this bead is going around counterclockwise on this hoop, and we want to describe this motion. What do we mean by this motion? That the bead is here, so the bead is actually at some location and this hoop is in some location, and whenever you are trying to mathematize, do not abstract and get yourself stuck in a mental frame and live in a mathematical space. You always have to look at physical reality first, and you always have to look at the physics of the problem. So the bead is actually somewhere in space and it is on a hoop. This hoop is also somewhere in the room, in the space, and this bead is going around on the hoop. And we are saying, just to make our problem very clear and very specific, we are saying that it is going around in a counterclockwise direction. It could be going any which way, and it could be going randomly. It may not be on a hoop, but we are starting with something simple so we can see how to mathematize. Now, you can pick any point that you want. You can pick a point here, you can pick a point there, you can pick a point anywhere, wherever you like. But clearly, there is certain problem to this, a certain symmetry to the problem, and you can see that all the points on the hoop would be at the same distance if you were standing at the center. Now, if I am standing at the center, I want to describe where this ball is going, how this ball is moving. So what I'm going to do is I'm going to look at my wristwatch, and I'm going to look at a physical change in my wristwatch. That is, the seconds hand is moving from one point to another point. That is a physical change. And I'm going to see within that physical change where this bead on the hoop is going. So the bead on the hoop is here, but it could actually be there. So being here is its actuality, being there is its potency. When the bead moves from here to there, that's when the potency is actualized, or there is change of place, and then there is motion. But in mathematics, we sort of abstract that away. We sort of abstract the change away, and we consider as if the ball is here and there at the same time. So we say the ball is here and the ball is there, it's gone there. And so to describe that motion now, what I'm going to do is, from where I am standing, I have to look at this ball in a certain direction. Only if I look at it in a certain direction can I see the ball. For example, if I'm standing here, but if I'm looking this side, then the ball is behind me and I don't see the ball. So I have to orient myself so as to see the ball. So what I'm going to do then is I'm going to orient myself such that I can see the ball, and I'm going to draw an arrow from me to the ball. There is no coordinate system. Never ever begin with coordinate systems. If you start with coordinate systems, no matter which coordinate system, you're handicapping yourself. So coordinate systems are a big handicap. So let's not think about it in terms of coordinate systems at all. Think about it only from the physics point of view, that you want to describe the motion, that is your goal. That is, you want to describe the change of place, the bead going from here to there. So you begin with looking at the bead where it is right now. And we're saying the bead is here right now. And so I see that the bead is at a certain distance from me. That is, there is physical space between me and the bead. And this physical space is not nothingness. It is something. It is a physical thing. And I am drawing an arrow to it. And I'm going to call it, I'm going to give it a name. I'm going to give it a name R, parameterized by some parameter T. This parameter T is given by my wristwatch. That is, I'm going to look at my wristwatch, and after my seconds hand undergoes a certain amount of physical change, that is, let's say my seconds hand goes from 12 to 1, that is 5 seconds have passed, then I look and check where the bead is on the hoop. So that would be my parameter. That is, every time my seconds hand moves by 5 seconds, then I'm going to look and check where the bead is on the hoop. And so I am trying to get, when I say r of t, and t is the parameter, I change this t parameter. That is, I wait 5 seconds, then I wait 5 more seconds. That is, a physical change is happening. My seconds hand is moving by 5 seconds. And then I draw a vector, or I draw, let me not say a vector, I draw something towards the ball in my mind and look at how far the ball is from me. So after 5 seconds, let's say the bead has moved here, then I have now a new arrow, that is r of t plus delta t. That is, after my parameter, I change my parameter by delta t, that is 5 seconds, let's say, then I'm remeasuring the direction, the orientation of where the bead is. And as you can clearly see, right, the orientation of my r has changed. That is, when the bead is here, my r is pointing in this way, whereas when the bead is there, it is pointing in a different direction. So now I am going to construct a unit vector. A vector, we haven't defined a vector, and a vector is something that has a magnitude and a direction. So here it is the physical distance between me and the ball. There is a certain direction, because only in one direction there is a straight line passing through me and the ball. If I change that direction, the straight line will either pass through the ball or through me. But for the straight line to pass through me, that is the reference point, and the bead, we need to be along a particular direction. That is, wherever the ball is, we need to look along that particular direction. Only then that line will pass through the reference point and the object. That's what we mean by orientation. And the ball is actually at some place. It is here or there or wherever it is. So it is in some place. And we are right now abstracting environment out, in the sense that we are considering that this environment itself is not affecting the motion of the ball. That is, we are not considering air drag. We are not considering friction. We are sort of abstracting this out. And then the ball is moving from here to there. So there is a change. And so there is time as the duration of that change. And so now what I have done is I started mathematizing this by using this thing called vector. This vector is coming from the fact that every physical thing has a place and it has an orientation. Whether it is a property or whether it is a physical substance, every physical thing has a place and an orientation, and that's why vectors become a natural way. And when you consider environment, that's when tensors will come, as we will see in a minute. But right now you can see that this bead has a place and it is along a certain direction from the reference point, so it has orientation. So then we have built a vector then that has something, there is some distance between me and the bead, and it is in a particular direction. And from this vector, we're going to build a unit vector. Let's say r hat. This unit vector is essentially a vector that is pointing towards the bead, but has only one step magnitude, whatever the unit may be, 1 unit magnitude. And the way we build it is we take this vector r and simply divide it by its magnitude. So we built this r vector, r unit vector. So we can write then the r vector itself at any time as the magnitude of r. I'm just going to write as r without an arrow times r hat. That is, at any given point, the bead is at a magnitude r away from the reference point, and it is in a particular direction. For example, at any given time, if this person is here, when the ball is here, if you look in this direction, you don't find the ball. So you have to look in this direction. That direction is specified by r hat. And r is how far you have to see. And so, as you can clearly see, this r hat itself is a function of time. That is, as the bead goes from here to there, the orientation of the ball is changing. that is the direction in which the ball is with respect to me is changing. And so this r hat is a function of time. So let's look at this more closely as we mathematize. So I have a bead going on a hoop and I'm trying to mathematize it. So to begin with, the bead is here. So I drew a vector and called it r hat of t. And I built a unit vector r hat that is given by r divided by magnitude of r. So we wrote r as r times r hat, and r is a function of time. That is, again, recall that I have a wristwatch. This time is a parameter. It's a parameter. It's not absolute time. I'm looking at a relative change on my wristwatch. I'm just looking at where the seconds hand is now, and when it moves from 12 to 5, I look at the ball. So I'm using one change to compare another change. One change is the seconds hand moving in my watch. Another change is this bead on the hoop moving from here to there. So I'm just comparing two changes. So because this r is parameterized by t, when I change t to t plus delta t, the ball goes from here to there. And so my r vector changes. But this r vector is not changing in terms of magnitude. It is changing in terms of direction. So this r hat is also a function of time. Now, we wrote that r hat is a function of time, but really this r hat is just pointing to the bead wherever it is. And as I change this parameter time, that is, as this parameter time is varied, when I look at the first 5 seconds, then the next 10 seconds, what is actually changing in reality is the direction in which the ball is from me. So the bead is here along this direction, then the bead is along this direction. So the direction is changing, the orientation is changing along with the place of the ball. So when the ball changes place from here to there, its orientation is changing. So r hat is dependent on time through direction. And so to note the direction, we can draw a horizontal line and say this is the angle theta. So if you go an angle theta from this horizontal line, you would have the direction along which the bead is present. So we can actually write r hat as a function of t as a function of time. So this is different from a normal function. What does a normal function do? If you take y of x, it takes in a number, x is a number, your input is a number, it assigns, let's say y of x is equal to x squared. Then it assigns another number. So it is a map of one number to another number. For example, if I say x is equal to 2, then you plug the 2 into y of x. Y of 2 would be 2 squared, which is 4. So it took a number 2 in and it assigned a number 4 to y. So that's a normal function. This function is different. Why is it different? Because at every theta or at every time, you are not assigning a number, but you are assigning a vector, something that has magnitude and direction. So when I say, let's say, a vector a time as a function of time, this is not a map of a number to a number. This t would be a number, a parameter. You take the parameter, and at every parameter, you're assigning a vector. So this function a of t would be a bunch of vectors. So for example, if I were to say, what is this position vector r of t for t going from 1 second to 10 seconds? And let's say we take in the interval of 1 second. Then we have at 1 second, we have one position vector. At 2 seconds, we have another position vector. So on and so forth. So for 10 seconds, you have a certain number of position vectors. You don't have numbers. So a vector function is not like a normal function which assigns a number to number, but it is assigning a vector to each thing. That's why we call this a vector field, because you have a bunch of vectors now. It's not just a function, it's rather a field, because at every parameter you have a vector. So this is the field of r hat vectors. That is, the physical change is my wristwatch. As my wristwatch goes from one point to another point, that is 5 seconds have elapsed, then the direction of the ball is changing, and so r hat is changing. So then now if I want to capture the rate of change of r, then I need to know dr by dt. But dr by dt is d by dt of, we have seen that r is simply r times r hat. So then this would be dr by dt r hat plus r dr hat by dt. We know that the first term is 0 because we have said that the radius of the hoop is not changing. We need to figure out what this dr hat by dt is. So dr hat by dt, we saw that we can write r hat as a function of theta as a function of time. So this would be dr hat by d theta times d theta times dt. What this means is when I change the parameter t, the angle changes. That is, the angle goes from theta to theta plus delta theta. Because the angle has changed, my position vector, which was pointing this way earlier, is now pointing this way. So I changed time, so then, or time changed, so theta changed. When theta changed, r hat changed. And you can look at this dr hat by d theta. So this dr hat by d theta, to see what that is, let's look at the hoop again. Again, I don't want you to think about this as a polar coordinate system, because again, that polar coordinate system is also a handicap. We are building r hat as something that is natural to the problem. It is not a particular coordinate system that you have to use. It is whatever is the problem. You have built that r hat unit vector from the problem. That is, you pointed to the bead and built it. For example, if this hoop were rotating, or if this hoop was extending and contracting, whatever it is doing, you can still do exactly the same way. And we will generalize it in a minute. So when I say we are trying to find out dr hat by dt, and that is, we saw dr hat by d theta and d theta by dt. So when you look at dr hat by d theta, the question we are asking is, for example, the bead is here. I moved it by some angle, let's say delta theta, and the bead has gone there. So I want to find out what is the change in the unit vector r hat when the theta has changed by delta theta. So what I want to do is, I want to bring this delta theta to a limit 0. That is, I want to bring these two things very close. So when I bring these two things very close, what I am in a sense doing is I am zooming into this part of the hoop. And if you zoomed in deep into this part, how would this part look like? It would just look like a straight line that's going up. If you zoomed into this part, this would look like a line that is horizontal. Again, this would look like a line that is like that. If you zoomed in, it would look like that. And we started with saying that the ball is going counterclockwise, so we give it a direction. So this is dr hat by d theta, and we can give it a simpler name called theta hat. And because the ball is going counterclockwise, it would be this way here, this way there, that way here. So then this would be theta hat d theta by dt. And so this d theta by dt is what we call as theta dot. That's just another symbol. So theta dot theta hat. So we started with trying to figure out how the position vector, this is the position vector r of t of the bead, is changing, and we saw that came out to be dr by dt r hat plus r dr hat by dt, and we saw that this goes to 0 because the radius of the hoop is not changing, and we saw this dr hat by dt should be r theta dot theta hat. So it is the position vector that is important. I don't want you to think about position vector in a coordinate system. A coordinate system is a secondary way of looking at a vector. In its primary way, a vector is something you are looking at, describing something physical, and that has some place or orientation in your makeup, and that's what you're looking at. You don't need a coordinate system to work with vectors. So we have seen how to get dr by dt. Now you can do the same thing to get acceleration. You can do d square r by dt squared. So that would become dr by dt theta dot theta hat plus r d theta dot dt theta hat plus r theta dot d theta hat by dt. And again, this term is 0 because the radius is not changing. The angle is changing. We don't know if it is accelerating or not. So we're just going to call this term, because it is a time derivative of theta dot, we're going to call it theta double dot. It's just a symbol. So for y of x, if you do dy by dx, we call it y prime. It's just a simpler symbol. So similarly, when we do dy by dt, we give it a name y dot. The dot is a simpler symbol to indicate a time derivative. So two dots indicate a double time derivative, because this is d theta dot by dt. So this would be then r theta double dot along theta hat plus r theta dot d theta hat by dt. Now we have d theta hat by dt. Now notice that this theta hat is the vector that we got from dr hat by d theta. So this theta hat clearly is also dependent on theta. That is, if the ball is pointing in this way, then theta hat here is pointing up, here it is pointing to the left, here it is pointing down, here it is pointing to the right. So this theta hat itself is changing as the angle changes. So to figure out d theta hat by dt, we're going to write theta hat itself is a function of theta, which is function of time. Because we have to always go back to physically what is happening. Physically, I have a parameter time. When that changes, the angle at which the bead is on the hoop changes. And when that changes, you have r hat change. And we have seen how that happens. And from there, we have seen that there is dr hat by d theta. And this is what we call as theta hat. But the theta hat is also still a function of theta, because this r hat is still a function of theta. So whatever is the result is still a function of theta. So on the hoop, when the ball is here, theta hat is pointing this way. When it is here, theta hat is pointing this way. When it is here, theta hat is this way. When it is here, theta hat is this way. So as you go around, as the angle changes, the theta hat is also changing. So d theta hat by dt can be written as d theta hat by d theta by dt. So you change time, theta changes. When theta changes, theta hat changes. And you can do simple geometry. For example, if I take this vector and this vector, these would be at different theta hat at two different thetas. So one is pointing up, and let's say another is pointing somewhere in the middle this way. Then if you do the difference, you can see the difference would be pointing this way towards the center of the circle. So by simple geometry, we are not using again any coordinate system. We're just manipulating vectors by themselves. So if you do that simple geometry, then this would figure out to be minus r hat, because r hat is pointing in the positive direction. Here, if I take this as theta at this point, theta hat at this point is pointing up, and here it is a little bit slanted. So if I take those two, the difference is pointing towards the center. And towards the center is minus r hat, and this d theta by dt is just simply theta dot. So then we can go back to our expression that we were trying to get for acceleration, d square r by dt square, and we had the first term as this, r theta double dot theta hat. I hope you're able to follow me. I apologize if I'm going fast or slow or whichever way. If it is not clear, please stop me and ask. And then we have the second term, r theta dot, and d theta by dt. That is the term that we had here, d theta hat by dt. And that we saw is minus r hat theta dot. So you can simplify this and you would get r theta double dot theta hat minus r theta dot square r hat. So far we have not looked at the causes of motion. All that we did was we mathematized the motion. That is, we said the ball is here, so let me draw a vector to it and let me see how this vector is changing. And just from simple physical arguments, we mathematized it, and we were able to derive the expression for acceleration and velocity. We don't know what is causing this acceleration and velocity. We don't know what is the cause of it. Nonetheless, we were able to capture something in this mathematics. That is, motion is change of place. When there is change, there is a cause, because nothing can change itself. So if something is changing, there must be a cause, because nothing can change itself. So if there is a cause, that cause we have not yet got into it. We have not yet said what is Newton's laws, how a ball begins to move, what is keeping it moving. We have not looked at all those. Nonetheless, just by looking at how the bead is moving around the hoop, we were able to get expressions for how this, we were able to first build an expression called R vector that is pointing to the bead. Then we built a unit vector that comes naturally out of it. And then we basically made a system where we could get the general expression for velocity and acceleration. Any questions so far?
Just a comment.
Yeah.
You're saying that you're not bringing in the coordinate system, right?
We're not beginning with a coordinate system.
You're bringing in any coordinate system here.
We are building what is natural to the problem.
No, you're not bringing any coordinate system in this.
What do you mean by bringing?
No, you're saying that we're not looking at any coordinate system, right? Movement in a coordinate system.
I mean, a coordinate system is a mental construct, so a coordinate system really doesn't exist. So what I'm saying is, look at the physical thing that is moving, and what is moving, you build a natural parametrization from it.
No, because see, the fact that you're talking about motion about a point, automatically that brings in a coordinate system. Huh?
No, it does not. A point is moving in physical space. There is no coordinate system in physical space. That coordinate system is...
When you say it moves about a point, then of course that is with respect to you taking it as some reference point, right?
Again,
so automatically that is...
There is no point in reality. In reality, there are physical things. It is physical things that move. So you are abstracting the extension of physical things away. You're talking about physical things as if they have no parts, which is what a point is. That is the first definition of a point in Euclid's Elements, that it has nothing, no parts. And so you're abstracting it out, and then that abstraction itself, you're building it in a coordinate system. But you have to sort of give up that mental picture first and look at things the way they are. It is a bead that is moving, and this bead is a physical thing that has one part outside another. It is going from one place to another. That is the actual motion, and that's what we want to describe.
Your reference point is the center of the hoop, right?
A reference point can be anything. A reference point can be on... Sorry?
Yeah, but that itself is some coordinate system.
No, that is not a coordinate system. A coordinate system is defined, it is not defined with respect to a reference point. That is just the origin. That is where I am standing and looking at it. Right? That's my viewpoint.
Yeah, it's origin.
It's
so
my viewpoint.
Origin,
yeah. But
so I think you're bringing in a coordinate system, I feel.
So
okay, continue.
Okay,
continue. Yeah.
So we are standing at an origin, and we are not drawing any specific directions. I'm not drawing any specific direction called X, Y, Z, and saying there are these three things, and this ball is moving this way, and I will reduce the motion of the ball to these three directions. We are standing at a particular place, the ball is moving, we are looking at the ball. It could be whichever way you are looking at it, from above, side, below, wherever, or from another planet. It doesn't matter. And you build a vector, that is, you are pointing to a particular direction. And at every time, you are assigning a vector to the position of the ball. So it is not a function like y of x that is built in a coordinate system. It is a set of vectors that you are collecting. So every time, wherever the ball is, you have a vector and you are collecting that vector. So you are actually having a vector parametrized. What you have is a vector field. So anyhow, so now...
Krishna, this r theta when you use, automatically you are bringing in polar coordinates.
These are not polar coordinates, sir. That is how you probably have been taught and you probably have assimilated it has polar coordinates, but this r and theta are just simply some variables that I am picking that are natural to the problem. I am not starting with a coordinate system. Here r and theta have no meaning without the bead. So r is pointing towards the bead. It is not an independent coordinate system that is started with the construction and then I'm assigning this r hat to the bead. I'm starting from the bead and drawing a line to the bead and saying that this direction of the bead is what I'm calling as r hat, and this is changing with time. So at every point I have a different vector. So I have collected a bunch of vectors that are dictated by the problem. So if that's how the problem is, then you know, that's the vectors that you get. But as I will show you, it doesn't have to be r hat theta hat. It could be anything that is dictated by the problem. And that's a different from coordinate system, because in a coordinate system approach, what you do is you begin with polar coordinates as if this polar coordinates have some existence outside the physical object. And then you say, I am putting this, my problem into polar coordinates. But that's not how the coordinate system comes in. We are building the coordinate system. We are not beginning with the coordinate system. So at the end of this, I have built the coordinate system, but I have not started with the coordinate system. That's the main distinction that one has to note. That at the end of it, I have built it in such a way that I got how this dr hat by d theta is changing, how the ball is changing, and then I have built how this d theta hat by d theta is changing, and by building that, I have gotten here. I didn't begin with a coordinate system.
No, but just a convenience which teachers use for teaching. Okay, they begin with the coordinate system actually, but then it's just a convenience for teaching.
No, that is actually very bad.
That is my view. That is my view.
Yeah,
okay.
that is very bad, because it sort of handicaps the students, because anyhow, I will show you how easy it is then to get in any general motion. Now, let's say the bead is not moving on a hoop. There is some physical thing. It's moving whichever way it is moving. We don't know whichever way it is moving. It doesn't have any rhyme or rhythm to it. It's just moving. Let's say it's moving something like that. It's going, we are not worried about causes. There is a ball, and this ball is moving in some fashion like this. This is not a physical hoop. This is just the path of the ball. That's how the ball is going, and I want to describe this motion. Then I pick a point, I draw a vector, I call it r, and I can parameterize this curve in time. That is, I'm measuring time and I'm seeing where the ball is at next time, and then I can draw another vector, and then I can draw another vector wherever the ball is, and the tips of all these vectors is what this curve is, and that's what we are parameterizing as time. That is, when the time changes, this r position vector is changing. Now you can write this r position vector as a function of something, and we are going to see what we can write it as, right? So you can pick whichever ones you want. You can pick whichever parameters you like, because this curve is clearly two-dimensional. This curve is clearly two-dimensional. So you would need two parameters to parameterize it, right? So when we say two-dimensional, we still don't need a coordinate system, because when we are looking at two-dimensional, what we mean is that there are two directions to it. That this curve is not changing in one direction, it is changing in two directions. It's going up and down, but it's also going forward. So we still don't need a coordinate system for that. That's just the direction. It is changing in directions, two directions. So let's say we pick something called z1 and z2. These are some parameters. We don't know what these parameters are. We're just in general saying this could be r and theta, this could be x and y, whatever you want it to be later. But in general, these could be anything, and these are functions of time. That is, as time changes, somehow these parameters change. That is, the ball moves from here to there, and now you have a new position vector. So then now, if I want to get velocity, that's simply dr by dt, and this r is dependent on z1 and z2, so I can write that as dr by dz1 by dt, plus dr dz2 by dt. So we can follow Einstein's convention, that is instead of writing this twice, it is the same expression except we changed 1 to 2 here. So we can combine that and simply write it as dr by dzi by dt. And this dzi by dt, for example, in the case of bead on a hoop, this is what we saw was theta dot. And here we can just give it some name. Let's say we give it a name vi. And if you look at this, dr by dzi, r is a vector. And because r is a vector, whatever the derivative of it is also a vector. Recall that a vector is different from a function. That is, you are assigning a particular vector field that is given by a specific parameter. So then what we have here is that we are going to define now from the physical problem, we will define this as a coordinate vector z1 or zi. That is, if I have dr by dz1, then this is vector z1. If I have dr by dz2, this is my vector z2. So my velocity v can be written as vi zi. Whenever you have a repeated index, it is summed over. So what this means is v1 z1 plus v2 z2. And z1 would be dr by dz1. For example, in case of the bead on a hoop, z1, we had only one coordinate, which was theta. So dr by d theta, right, would give us, from there we got the theta hat, right? And if you took this to be r, then you would get r hat. So dr by dr would give you r hat. So we are building a coordinate system or a covariant basis. So this zi is what we call as the covariant basis. So by starting with how the position vector is changing, we didn't start with the coordinate system, the ball or whatever object is moving, and the way it is moving, we're parameterizing with time. And we say if it is moving in 2 dimensions, then there are 2 different directions it can move in. If it is moving in 3 dimensions, there are 3 directions it can move in. So we can just start with r as some zi, that is z1, z2, z3, or whatever. If you have 2 dimensions, only z1 and z2, which themselves are functions of time. Then we build our own unit vectors. We build the first unit vector called z1 hat as dr by dzi. So then our velocity dr by dt v would simply be dr by dzi and dzi by dt. This dzi by dt is vi, and this dr by dzi is zi. So then we are writing this as vi zi. Now if we want to get acceleration, then we need dv by dt. So we need d by dt of vi zi. Now here these zi's are the coordinate system that we built, the unit vectors that we built, and these things are changing as time changes. For example, if you looked at bead on a hoop, right, as time changes, r hat is going from here to there when the bead moves here. So these are not constant, these are not some fixed things in space, because we are just trying to follow the object. So as the object changes, whichever way it is moving, when the object moves, it goes from here to there, so its position vector changes. So these parameters, these unit vectors we have built are changing, because this unit vector, we built it from r. and r is the position vector that is pointing to where the object is. So if the object changes from here to there, r changes. If r changes, then zi could change. So then we would have to write this as dvi by dt zi plus vi dzi by dt. Now when I look at this dzi by dt, for example, we built a unit vector r hat and we had to look at dr hat by dt, and this dr hat by dt we saw was r hat was in fact changing with respect to the angle, and angle was the thing that was being parameterized. When my time changes, angle changed, and angle changing changed r hat. Using that, we can write this dzi by dt as dzi. R is changing with respect to theta, so we would write dzj. We are just using j to show that it's a different index, and then dzj by dt. This is just like theta dot here. Now this one, if you look at this dzi by dzj, what that is in a little more detail, then we would get basically the entire expression for acceleration, that is dvi by dt along zi plus vi dzi by dzj by dt. Now look at this. For example, previously we had built two vectors, r hat and theta hat. This r hat was dr by dr. This theta hat was dr by d theta. That's how we build those. And now when I say this dzi by dzj, that means I have r hat. So I would have, for r hat, I would have dr hat by dr or dr hat by d theta. So for each zi, I have those many vectors. So this is a set of vectors that we are getting. And this is what is called as the Christoffel symbol, or the vector notation of the Christoffel symbol. So we can actually write this, because these are also vectors. This dr hat by d theta is a vector theta hat, right? So I can express it in terms of theta hat again. So I can write this dzi by dzj as something called Christoffel symbol, which is given by gamma. We write it as gamma ij zk. We'll talk about this more in the next chapter, the next module, but this is what a Christoffel symbol is. Now so far what we have done is we have seen how an object is moving. Just from there, by parameterizing that curve, we defined a covariant basis that is natural to the problem. We didn't begin with a coordinate system again. We began with the object moving, and we were drawing position vectors to it. And by drawing position vectors and collecting all those position vectors, we naturally established a covariant basis. And from that covariant basis, we got expression for velocity, and then we got expression for acceleration. So you can see clearly that acceleration is not just dv by dt. You also have to consider how the basis itself changes. And this is very, very important, because as physics students, when we say I can draw a straight line from wherever I am to wherever the object is, you are inherently assuming that the space around you is Euclidean. That if I can draw a straight line from one point to another point, that is, this entire space around me is flat. That's why I'm able to draw a straight line. So if I'm from here to there, I can draw a straight line like this because it is flat. For example, if you are on the top of a surface like sphere, if you want to draw a line from here to there, you cannot draw a straight line. You have to go along the surface. It's a curve. So a straight line on that surface would be a curve. It's not really a straight line. When you say straight line, that wherever the object is, wherever the bead is, wherever the ball is, I'm able to draw a position vector to it. I'm able to draw a straight line to it. I'm assuming inherently that I am in Euclidean space. But it is not necessary that for us to be in that particular space. So how do we bring in this space? So far we have looked at where the ball is, whether it is here or there, that is its place, which direction it is in. By combining its place with the direction, we have built the position vector. From the position vector, we constructed covariant basis. From the constructed covariant basis, we got velocity and acceleration. But we had excessively abstracted environment out. We have not really considered what is the environment between me and the ball. Are we embedded in some sort of flat Euclidean space, or are we embedded in some other thing? Like, for example, if we are on the surface of Earth, then obviously, you know, I cannot draw a straight line because I have to go along the surface of Earth. So that's not really a straight line. So can I draw straight lines? And if I draw, whichever way I draw, what is this environment? How do I know, you know, based on the line that I am drawing, based on this position vector that I am drawing, by looking at how this position vector is changing, how can I know whether I am in Euclidean space or I am in a space that is curved? And that's why these Christoffel symbols, the way they change, as we will see, with time especially, the way these Christoffel symbols would change with time, has everything to do with how space is curved. So this way of teaching, when you introduce mechanics from this, by putting physical things first, by introducing place, orientation and environment, naturally leads to the question of general relativity. It naturally leads you to think about, can I draw a straight line always? The answer is no, because the space in between is not nothingness, it is something, and it changes a certain way with time. So you cannot really draw straight lines. So these lines are curved, therefore space-time is curved, and we will see later that this naturally flows out of these Christoffel symbols, that it jumps out at you. So with that, I would like to stop here and wrap up the lecture as vectors come from the fact that physical things have place and orientation, and tensors determine how these vectors change in the environment. So tensors describe place, orientation and environment, whereas vectors describe only place and orientation, and a scalar only describes place. So if you just take place scalar, place and orientation vector, place, orientation and environment a tensor, and then if you consider place, orientation, environment all along with time, you would have time dependent scalars, time dependent vectors, time dependent tensors. So by putting physical things first, the physical meaning of vectors and tensors comes out more clearly, and then you can look at how things like even space-time curvature jump out at you from this simple thing. So with that, I stop here. Thank you.